Hey folks, I'm coming back to you now with continuation of section 6.4. As you can see on my screen, this is the problem that I originally referenced in the first video, number 5 on page 272. As we remember, we had a mean for the population that was 74 beats per minute, standard deviation for the population that was 12.5 beats per minute. Part A was asking us to think about if one adult female is randomly selected, we need to find the probability that her pulse rate is less than 80 beats per minute. As I mentioned on that first video, folks, that's no different than what we would have done originally. We would go into StatCrunch, insert our mean and standard deviation, and calculate our area under the curve for selecting an individual whose pulse rate is less than 80 beats per minute. So let's go over to StatCrunch and take care of that. Remember, we come over to Stat, Calculators, Normal, just as we did in section 6.2 and 6.1. We're going to insert our mean, which in this case was 74, our standard deviation value, which was 12.5, and then this particular problem was asking us for a probability that her pulse rate is less than 80 beats per minute. So we're going to use less than or equal to 80, and then we compute. And then you can see that our probability of selecting that one female whose pulse rate is less than 80 beats per minute is at 0.684 or 68.4% chance that we're going to select an individual female whose pulse rate is less than 80 beats per minute. However, as I referenced earlier in the first video, Part B is getting us to think about not selecting one. Remember, we're selecting a group. So when we select that group, we need to make sure that our central limit theorem requirements have been met, in which we did earlier. Yes, we know A, that the population from which we're selecting is normally distributed, as mentioned in the opening of the problem. B, if we don't know that that population is normally distributed, then we need to have a sample size that's greater than 30. Well, Part B is not a sample size that's greater than 30, but since we know that the original population of female pulse rates is normally distributed, we're good to go. So then we are going to insert the mean of our population, which in this case was 74, for the mean of all sample means. However, that standard deviation of sample means needs to be adjusted to where we take the 12.5, which was our standard deviation of the population, as I showed earlier, and divide that by the square root of the sample size, which in this case, the group we were selecting, was 16. Now we'll come over to StatCrunch and find it. Pretty easy. We're going to change and keep our mean at 74 beats per minute. But this is where I told you we need to take our standard deviation of the population, divide it by the square root of 16, which 16 is a pretty perfect square, and we can insert 4 because the square root of 16 is 4. And we're still looking that we're going to select that group of 16, and I want to know the probability that their mean is less than 80 beats per minute. So let's click compute. And there you have it. You see that our probability value here is going to be 0.973 if you round it to 3 decimal places. So realistically, it's not any different from the calculator perspective, but it's very important to know that our central limit theorem is helping us think about moving forward with estimating population parameters when we move into chapters 7 and 8. Let's try another one. Let's come back over to eText. And let's go and think about, on page 273, bear with me just a second as I get this to work with me. Okay. I want to get us to think about number 13. Number 13 is really a good application problem for our central limit theorem. As you read there, you can see that we're considering water taxi safety. Passenger died when a water taxi sank in Baltimore's Inner Harbor. Men are typically heavier than women and children. So when loading a water taxi, we're going to assume a worst case scenario in which all the passengers are men. Assume that the weights of men are normally distributed with a mean of 189 pounds and a standard deviation value of 39 pounds. The water taxi that sank had a capacity of 25 passengers, and the boat was rated for a load limit of 3,500 pounds. Part A. Given that the water taxi that sank was rated for a load limit of 3,500 pounds, what's the maximum mean weight of passengers if the capacity of our boat is stated at 25 passengers? So like, uh-oh, we got a lot going on this problem. We got to figure out what's going on. Well, first of all, we know that it cannot exceed 3,500 pounds. And we know that it cannot hold any more than 25 passengers. So I want to know what's the maximum mean weight for that particular passenger. Well, if we evenly distribute out that 3,500 pounds over 25 passengers, because we don't know who the passengers are, we don't know what their weights are going to be. We have to operate under the assumption that the load limit is 3,500 pounds. We're going with the men. So if we were to think about how much each one of those men could maximally weigh, we need to take, and first of all, take our 3,500 pounds. I'm in Desmos for calculator purposes. And then I'm going to divide that by 25 because 25 references the maximum number of passengers, which then we have to evenly distribute that out among those 25 passengers, knowing that the maximum weight capacity is 3,500 pounds. So we see that no more than 140 pounds per passenger is going to be in check with the load limit of 3,500 pounds. Okay, now that's part A. Let's go back to part B. Part B now gets us to think about if the water taxi is filled with 25 randomly selected men. That's the group that's being selected. What's the probability that their mean weight exceeds the value from part A? So essentially, we're looking for what's the probability that their mean weight exceeds 140 pounds. I'm going to write this down so I can remember real quick. Now, come back over and let's identify what the mean for the population is, what the standard deviation of the population is, and let's think about, can we use the central limit theorem to help us in this calculation for this specified probability value? Well, when we go back and read, they do tell us that we are to assume that the weights of men are normally distributed, winner, winner, chicken dinner, so we can move forward with central limit theorem. Because it's not population normally distributed and the sample size is greater than 30. It's population is normally distributed or you need a sample size larger than 30. And you'll notice that our sample size that we're choosing is 25, which is less than 30. However, since we know that our weights of men are normally distributed, we can move forward with our central limit theorem. So then that tells us, and I'll show you what I'm getting ready to write down, that we can use our mean for the population to represent the mean of all sample means, which they told us that mean was 189 pounds. However, when we think about the standard deviation of all of those sample means, we need to take our standard deviation of the population, which was 39, and divide that by the square root of our sample size, which in this case was 25. So this becomes what we are trying to focus on inside of StatCrunch. Oops, there you go. Now you can see 39 divided by the square root of 25. So I want to begin by simplifying that standard deviation of all sample means. I know 39 divided by the square root of 25, square root of 25, yay, is a nice, pretty, perfect square. So we can change that square root 25 to the square root value, which is 5, as you can see there. So now we move over to StatCrunch, and remember the probability value is, we want to know what's the probability that their mean weight exceeds the value that we found in part A, which was 140 pounds. Here we go. StatCrunch helps us out. So let's insert our mean of 189. Let's insert that adjusted standard deviation value and show it as 39 divided by 5. And we want to know what's the probability that it exceeds. Then that implies greater than or equal to our value from part A, which was 140. And we'll compute. Whoa, that's problematic. You're like, why did you say whoa? It's almost a given that if we were to take all of those 25 men and put them on that boat, guess what? They're going to exceed the capacity of the boat. That's what we were working with on this case. You're like, well, why would you say whoa? Would you want to be on that boat? You want to ride that boat if you know that you've got 25 men, and when you look at their weight, and if we assume 140 pounds for each of those men, I don't think that boat's going to make it up the harbor. Therefore, I would not want to ride that boat. It's not safe. So, let's talk about adjusting it a wee bit. So what they get us to think about in Part C is, erase on my little board here. After the water taxi sank, the weight assumptions were revised so that the new capacity becomes 20 passengers. So now we're selecting a different group from the population. We're going to select a group of 20. If the taxi is filled to 20 randomly selected men, what's the probability that their mean weight exceeds 175? The 175 value was generated in a similar fashion. They take that 3,500 and divide it not by 25, but we're going to divide that by 20. See, there's your 175 value that they're coming up with there. Easy peasy. So, we're still wanting to know what's the probability that their mean weight exceeds 175 pounds. So this go round, we're exceeding 175 pounds. We're still going to assume that the mean of the population is going to be the mean of all the sample means, which in this case was 189 pounds. And now our standard deviation of all of those sample means is going to become 39 divided by the square root of 20, as you see here. Oops. Can you see it? Hey. So, square root 20 is not a nice, neat, pretty, perfect square. So I'm going to let Desmos help me out a little bit. And let's delete this out. And let's insert 39 divided by square root 20. And you see you get a value of 8.7206665. Just carry as many decimal places as you can. I wrote it down on my little whiteboard so I can take and fill it in. Or, let's see if I can get a little savvy. Let's take and do Control Copy. Let's come over to Stack Crunch and let's do a Control V. Yay. Looks like it worked. Yippee skippy. But we need to change this from 140 to 175. Ew. I still don't want to ride the boat with those updated parameters. I still don't think it's safe. You're like, well, why are you making these faces? Why are you thinking about safety? Because when we come back over to the interpretive idea that they get us to think about, that comes in Part D. Part D, they ask us to think, is the new capacity of 20 passengers safe? Well, hello, Marie. There's a 0.946 chance that with new revisions, the boat's still going to be exceeding the capacity for the safe load, meaning a 94.5 chance that the boat's going to be overloaded and it's going to sink. Not riding that boat in the Boston Harbor. I want to stay safe. So, these are the general ideas that they're getting us to think about in section 6.4. If you have further questions, I'm a message away, remind message away, email message. I'm happy to go over future problems if you would like for me to in a Google Meet or a Zoom chat or some sort of collaborate session. I'm happy to do that. Just let me know what you need and I'll do my best to help you out. Thank you and look forward to hearing from you.